Cambridge in England is often called the birthplace of modern science. It has produced many great thinkers, such as Darwin and Newton. Here, one finds another great thinker with a profound influence on the world today. Martin Rees is one of the world's foremost astrophysicists. Rees aims to apply theory to unlock the secrets of the history of the universe, from its origin to the present.
I think what is rather wonderful is that we are able, as humans, to make sense of our environment, to understand how we got here. Obviously, Darwinian evolution here on our planet, but we are able to put our planet, the Earth, in its wider cosmic context, to trace it right back to the origin of the solar system, the origin of the galaxy, and right back to the first tiny microsecond of the Big Bang that set everything going.
This is how Rees believes the universe came into being. It is thought that the universe began 13.7 billion years ago. It all began with the Big Bang. The newly created universe started off in a high-energy state, filled with light. This was the Age of Light. Once the universe had cooled down to 6,000 degrees Celsius, helium was created, and at 3,000 degrees, hydrogen. Temperatures continued to drop. The universe became filled with just hydrogen and helium. As time passed, the visible light that had once filled the universe gradually stretched to longer wavelengths, and by around 500,000 years after the Big Bang, there was no light left that could be seen. This marked the end of the Age of Light and the beginning of the Dark Ages, according to Rees. Let's turn back the clock from the present to the beginning of the universe, 13.7 billion years ago. At some point along the way, all light is lost, and darkness envelops everything. How long these dark ages lasted and how they ended remains shrouded in mystery.
One of the things that I'm very interested in myself is how we can actually probe the way the first light happened in the universe, when the first structures formed and lit it up. Were these ordinary stars? Were they massive stars? Were they single? Were they in groups? And how did those develop into galaxies?
When did the first stars come into being, shedding light on the dark universe? And what kind of stars were they? Prompted by these questions posed by Rees, astronomers around the world are now attempting to observe the first stars. One scientist is trying to observe the first stars directly. For more than 30 years, Garth Illingworth of the University of California has been using telescopes to uncover the origins of the universe.
It's actually interesting because what we're doing here is searching for the youngest objects. And so with astronomy and our telescopes, what we can do is look back in time.
To look at the distant universe is to look at the past. Light emitted at a certain moment in the past travels at the speed of light. As light travels, time continues to pass. And so what the observer sees at a distance is not the present, but in fact, the past. In other words, When we see a star that is 10 billion light years away, we are actually seeing how it looked 10 billion years ago.
It's exciting to be looking out to the earliest possible times. One of the things that is behind all of what we do is trying to understand our place in the universe. And so as a person, I think I come to this with a desire to really understand our origins.
Back when Illingworth began his research, the largest telescopes were the ground-based 4-meter aperture telescopes. At the time, he and his colleagues focused on galaxies, the huge gatherings of stars, to observe the universe as far away in distance, and therefore in time, as possible. In 1990, this was the most distant galaxy that could be observed at the time. Observed at a distance of 7.8 billion light-years away, it showed how the galaxy appeared 7.8 billion years ago. Yet this was still just half of the universe's 13.7 billion-year history. It was around this time that the Hubble Space Telescope was launched.
Hubble was really a game changer in what it did for astronomy. Up to that point, we had telescopes on the ground that, while very powerful, were rather limited. When we look out through the atmosphere, it blurs. We can't see all different wavelengths. Taking a telescope into space was an amazing change for us. Suddenly, we had crystal clarity. There's no atmosphere.
In 2003, Illingworth and his colleagues set out to use the Hubble Space Telescope to observe the furthest reaches of the universe to date.
Okay.
The target of their observations was one corner of Fornax in the southern sky. Using ground-based telescopes, this area appears pitch black, with hardly anything visible. They thought that here they would be able to observe even dark celestial objects a great distance away. Hubble made observations of this one region over the course of 270 hours. This was the end result. "10,000 galaxies of varying sizes had been captured. Many galaxies more than 10 billion light-years away were also discovered. The Hubble Space Telescope has allowed humans to capture with such clarity the universe as it was 10 billion years ago. By looking out even further, it may be possible to observe the first ever stars that ended the Dark Ages. With this in mind, Illingworth set out to somehow find a way of observing the most distant celestial objects. The method he came up with was the layering over of images. He layered together 2,062 Hubble images captured in various observing programs. In September 2012, an image was produced showing the darkest celestial object ever captured. Illingworth proceeded to work out the distance of each celestial object in the image. He then singled out a dimly shining red object.
It is the deepest image of the sky. And so the one that is most exciting is this one, 6284, which is the galaxy that we first found 2 years ago, which is at redshift a little over 10, and then as a result is only 450 million years from the Big Bang.
The red object shows some spread and is irregular in shape. Illingworth believes that this is a galaxy made up of 1 billion stars clustered together.
One of the most interesting aspects of this whole activity of trying to see the earliest galaxies is trying to understand what came before, when the first stars and when the first galaxies formed and started to grow. And that was probably about 200 million years before this image.
Thanks to the Hubble Space Telescope, it has been possible to get a glimpse of the fledgling universe. Just 450 million years after the Big Bang. We are just one step away from finding the first stars that ended the Dark Ages. Looking into the distance is not the only way of searching for the first stars. Rees argues that with some ingenuity, one need not look far to find the first stars. Rees believes that among the first stars born more than 13 billion years ago, a few still survive, continuing to shine. The lifetime of the Sun is 10 billion years. A star with a mass 80% of the Sun can continue to shine for well over 13 billion years. It is therefore entirely possible that there are first stars still around us. Furthermore, Rees explains that the first stars have a distinctive feature not seen in other stars.
What we don't know is the masses of these first stars. We don't know how many there were. We don't know exactly when they formed. And that is one of the frontier areas of our subject at the moment. But first stars would form from material made in the Big Bang, which contains essentially only hydrogen and helium.
Immediately after the Big Bang, only two elements, hydrogen and helium, existed in the universe. It follows that if a light star made of just these two elements was discovered, it would be a first star that has survived to this day. One scientist is seeking to prove this theory by seeing if there are any surviving first stars near us. Anna Frebel has spent the last 10 years searching for a first star made up of just hydrogen and helium.
My research program focuses on finding the oldest, most matter-poor stars. And of course, the ultimate goal is to find a first star, a star that came first in the universe and changed everything.
Born and raised in Germany, Frebel loved stars even as a child. On becoming an astronomer, she came across the concept of searching for first stars and has been absorbed by it ever since. Frebel is currently carrying out observations at Las Campanas Observatory in Chile. She is aided in her search for the first stars by this telescope with its 6.5-meter aperture. Using special equipment, she analyzes the colors of the star's light and works out what elements and how much of them are found in each star.
Can we go to target number 8, please? This is a star that we observed earlier tonight, and this is one of the most matter-poor ones we found this run. What you can see is that the lines here, the strong magnesium lines, become much weaker. If it was a first star, we would see just continuum, no lines at all. But these are pretty weak already, so we're almost there.
Frebel can only make observations with this telescope 10 days of the year. To maximize the precious time she has here, observations are carried out non-stop until dawn. Frebel has observed 1,500 stars over the past 10 years, but she has yet to encounter a first star.
If you want to find the needle in the haystack, you have to be very persistent, right? We are looking for objects that are very, very rare. So you have to sift through lots and lots of stars, and hopefully you are lucky in the end. So you have to be very patient and very diligent and work very hard, but it's also a lot of fun. So you have to have fun as well.
Somewhere in this starry sky, a first star is shining, waiting to be found. It can only be a matter of time before it is discovered. Observational equipment, like ground-based giant telescopes and the Hubble Space Telescope, are being employed in the search for the first stars. The University of Tokyo's Naoki Yoshida, however, is approaching the problem with a method that does not involve making observations. Yoshida designed a computer simulation of the newly created universe to observe how the first stars were born. Just 380,000 years after the Big Bang, intense light was emitted all over the universe. By looking 13.7 billion light-years away, it should still be possible to observe this light as microwaves. In order to observe this light directly, the WMAP satellite was launched. The light from 13.7 billion years ago is observed from all directions in the universe. By measuring the differences in the intensity of the light, it is possible to find out how matter was distributed throughout the universe at the time. This is how the primitive universe looked at 380,000 years old. The red spots show regions of low matter density, while the blue spots indicate high density. We now know how the universe looked 13.7 billion years ago, just before the Dark Ages. With the starting point established, it's time to turn to Yoshida and his computer.
WMAP の観測結果というのは、私たちみたいに理論研究を行う研究者から見れば、宇宙の初期の状態を教えてくれるわけです。計算の話にしますと、宇宙の初期状態が分かるもいいかもしれません。言ってもいいかもしれません。
Working from the WMAP data, Yoshida used 300 million particles to represent hydrogen and helium, and recreated the infant universe in his computer. What looks like smoke are actually particles. The laws of nature that function between the particles should remain the same today as they were 13.7 billion years ago. Using 107 formulae, including the equations of fluid dynamics that govern the motion of gas, Einstein's equations for the expansion of the universe, and the equations for the chemical reactions of hydrogen and helium, Yoshida made accurate calculations of the particles' behavior. This is the young universe as recreated by Yoshida's computer. It shows, for the first time, how the Dark Ages looked. The hydrogen and helium that had been drifting about start becoming uneven in density. The gases begin to gather together under their own gravity and create a spider web-like structure. It took 7 years to attain these results. A spherical mass of gas has been formed, but no first star yet. To keep looking beyond this point, calculations within smaller time frames were necessary. And so 3 years were spent developing a new model to recreate what happened at the center of the clouds of gas. These are the results. The onion-like structure shows the density of gas. The density increases towards the center of the mass. Here's what happens as time passes. The density of the gas at the top and bottom decreases. Meanwhile, the gas at the sides does not decrease in density. The gas flows into the center, and the core becomes increasingly heavy. The gas continues to be compressed, and when the center reaches a searing temperature of 100 million degrees Celsius, nuclear fusion begins, and the universe produces a self-illuminating star for the very first time. This is the first star.
私たちのシミュレーションで明らかになったことは、その宇宙の始まりの頃に存在した水素とヘリウムだけからなるガスから確かに星が生まれました。でさらに計算を進めますと、どうもその星は、質量にしますと太陽の40倍から50倍ぐらいの非常に大きな星であるということが分かりました。
Yoshida's calculations showed that many of the first stars were massive stars that emit an intense blue-white light. They weigh 50 times the mass of the sun, and they are an outstanding 1,000,000 times brighter. Heavy stars burn up quickly, and so they only live a few million years. This is the story of the birth of the very first star, as revealed by Yoshida's computer model. "380,000 years after the Big Bang, an intense flash of light was emitted all over the universe. And then came the Dark Ages, when darkness reigned. During this time, only hydrogen and helium gases were present in the universe. There was some irregularity in the distribution of these gases. Gas was drawn into the denser regions by gravity, creating a cloud of gas. The temperature at the center became increasingly hot. When it reached 100 million degrees Celsius, nuclear fusion began, blasting off the surrounding gas. And so the first star was born. The temperature of the bright blue surface is 100,000 degrees Celsius. Its brightness, 1,000,000 times that of the sun. Emitting vast amounts of energy, the first star moves ever closer to its dramatic fate. A few million years have passed since its birth. The star bursts in a huge explosion, and it comes to the end of its life. This is the life of the first star, brought to light by the latest astronomical research. Yoshida's calculations have revealed the spectacular ending to a first star's life. The explosion lasts just a moment, but releases such an intense burst of energy that it may be possible to observe it, even if it happened more than 13 billion light years away. SWIFT is an astronomy spacecraft, launched in 2004 to observe massive explosive phenomena. When a huge star like a first star explodes, it emits intense electromagnetic waves called gamma rays. This phenomenon is known as a gamma ray burst. By detecting the abrupt appearance of gamma rays, SWIFT can seek out the massive explosions of stars. On April 29, 2009, SWIFT detected a 5-second long gamma ray burst in the constellation Canes Venatici. When a massive explosion is detected, researchers around the world are alerted immediately. The news sent a ripple of excitement through astronomers worldwide. Among them was Antonino Cucchiara, who was a student at Pennsylvania State University at the time.
We needed to act right away. The main reason for that is because we had access to Hawaiian telescopes, and I was in the East Coast, already was in night, so it was sunset in Hawaii. So the night was just started.
By turning a telescope to the explosion immediately after its detection, it would be possible to make detailed observations. At the time, Cucchiara was in Pennsylvania on the east coast of America. The telescope was in Hawaii, 8,000 kilometers west, with a time difference of 5 hours. The sun was setting in Hawaii when SWIFT detected the explosion. At the Gemini Observatory, on the 4,200-meter-high summit of Mauna Kea, preparations were underway for scheduled observations. Astronomer Kathy Roth was working in the lab when a target of opportunity alarm flashed up on the computer screen.
Attention, target of opportunity.
So at night when we're observing, if we receive a new rapid TOO alert, we interrupt what we're doing, the scheduled observation, so that we can focus on the new TOO, just like we did back in April 2009.
Roth stopped what she was doing in order to help with the target of opportunity observation. Two and a half hours after SWIFT had detected the explosion, a giant 8-meter aperture telescope was turned to its direction. The observations were carried out for 15 minutes. But nothing could be seen. It was this blank image, however, that excited Kukiara.
If you don't see anything in your optical images, it's already a sign that this object can really be one of those most interesting ones. So it was really exciting. Everybody was excited.
Light emanating from the distant universe of the first stars has its wavelength stretched by more than 10 times under the influence of cosmic expansion. This has the effect of changing the light into infrared waves invisible to the human eye. In other words, if this were a first star explosion, it wouldn't be visible as ordinary light, but only as infrared.
I think it was like 3 a.m. in the morning at that point. So it was kind of interesting because at that point my colleague in Europe and in UK were well awake. So I coordinated with them. We decided to go with another set of observation, the infrared.
Roth, meanwhile, was busy in the control room.
This is the raw acquisition image in the R band. And this is the finding chart. What you would expect is you would see an object here, which I don't see anything there. So we zoom in a little bit to look a little harder, change the stretch, but I still don't see anything here. So then if you take an image in the infrared, however, K-band in this case, then you start to see there is a faint object there.
If this explosion had occurred more than 13 billion light years away, it's possible that it was a star from more than 13 billion years ago. In other words, a first star. To calculate the accurate distance from the exploding star, Kukiara decided to carry out a third set of observations, using equipment that analyzes the colors in light. But luck was not on their side. The weather up on the summit, which had been fine up until then, suddenly turned. Clouds spread across the sky.
Actually, I think it was a phone call from one of the telescope operators saying, I'm sorry, but the clouds just roll over. We need to close the dome. And we were like, okay. I mean, we were like, it was really interesting, but there is something we don't have power on, and that's the weather.
The next day, the telescope was turned to the same spot again. The light was too faint, however, to carry out the intended observations. But Kukiara did not give up. Over the course of a year, he set out trying to work out the distance using the infrared images. When the infrared images were captured, several different filters were used. At wavelengths any shorter than in the filter labeled J, nothing can be seen. By analyzing the images captured by Gemini, they could work out the approximate distance from the celestial object.
The farthest you push an object in distance, meaning also in time, is very close to the beginning of the Big Bang, you're going to start losing information, you start losing light. First you lose the UV light and then the optical, and maybe you start seeing some losing light also from the infrared. And that means that the object is actually a high redshift, or means, like in this case, 500 million years after the Big Bang.
By observing many more distant explosions like this, scientists can determine when and how many first stars were born. Martin Rees believes that the appearance of the first stars transformed the course of history for the universe.
In order for us to be here, then lots of things have to have happened over the 13.7 billion years since the Big Bang. The first stars have to have formed, and they need to have led to nuclear fusion, transmuting primordial hydrogen and helium into elements like carbon, oxygen, and iron.
The first stars were born out of just the hydrogen and helium that existed in the universe at the time. Inside the first stars, nuclear fusion took place, creating elements like carbon, nitrogen, oxygen, and iron out of the hydrogen and helium. When the first stars meet their demise in an explosion, these elements are scattered throughout space. One scientist is making observations of the elements created by the first stars. Timothy Beers is searching for the second stars, the second-generation stars born just after the first stars exploded. Second stars contain elements such as carbon and oxygen that were created by the first stars. It was thought that the quantity of these elements would be just 1/10,000th of what is found in the Sun. Beers hopes that by investigating the quantities of elements found in stars, he will be able to find the second stars. In order to make the search more efficient, he employed a special method. The technique is called objective prism. By placing a giant prism in front of a telescope, the light of each star that had looked like dots appears as thin bands of rainbow colors. This is the spectrum created when sunlight is put through a prism. A closer look reveals faint black lines among the rainbow. These are caused when the elements contained in the sunlight absorb certain colors of light. These black lines are known as absorption lines. The Sun produces so many absorption lines because it contains huge amounts of many different elements. The second stars that Beers is looking for, on the other hand, contain hardly any elements apart from hydrogen and helium, which means there should be very few absorption lines. Beers used 2 telescopes in Chile and America to capture a total of 340 photographs. The glass photographic plates have been carefully stored. Each glass plate depicts 10,000 stars. Up close, absorption lines can be seen on most of the stars.
Once we take the plates with a telescope such as the Burrell-Schmidt, that's really only the beginning of the effort. We have to find the most interesting chemically ancient stars. With that microscope, we could determine whether a star was likely to be interesting or not.
Using this method, this candidate was singled out as a potential second star. It certainly shows almost no absorption lines. Such candidate stars were then observed through a larger telescope. This enabled Beers to pick out 1,044 second stars. This is a star located in Pisces. Its iron levels were found to be 1/10,000th of those of the Sun, which allowed Beers to conclude that it was a second star. A further investigation threw up a surprise. The carbon levels were 100 times greater than what was predicted. The first stars had produced a great quantity of carbon, which had then been passed on to the second stars.
One of the most exciting results of the last 2 or 3 years has been the recognition that the first stars produce very large amounts of carbon, nitrogen, and oxygen, the 3 fundamental elements without which, as far as we know, no life can be formed.
The various elements produced by the first stars are inextricably linked to the birth of ordinary stars like our Sun. This is the theory put forth by one researcher. John Weiss is working on a simulation of the universe after the first stars, incorporating the elements they produced. According to Weiss's simulation, the first stars themselves did not cluster together to form galaxies. A few 100 million years after the first stars were born, galaxies formed where the stars had been. How were these galaxies created? Let us study the simulation in more detail. The top half of the screen shows Weiss's simulation of the universe, while the bottom half shows the distribution of elements such as carbon, oxygen, and iron at the time. This is what happens as time progresses. As the first stars explode, huge volumes of elements are scattered in certain areas. A multitude of stars are created where there are high concentrations of elements, giving rise to galaxies. In areas with high levels of carbon, oxygen, and iron, small stars like the Sun are born one after the other out of these elements. Weiss believes these were the beginnings of the galaxies we see today.
These first stars, they produce the very first metals in the universe. And without these first metals, we wouldn't see any of the stars that we see today.
The explosions of the first stars changed the universe irrevocably. The explosions caused elements like carbon, oxygen, and iron to scatter all around. These became the building blocks from which a whole host of lighter stars, like the Sun, were born. These stars clustered together, forming galaxies. In other words, these first stars paved the way to our present universe, full of stars and full of life. The first stars brought light to a dark universe. It's thanks to these first stars that the universe we know is filled with light and a multitude of elements. Stars like the Sun and life forms like ourselves can all be traced back to the first stars.